We are going to create a swim storm drainage and flooding network from scratch. The instructions for this exercise are given uh, in the document that is provided to you here, instructions. So um, the we are going to create a hypothetical storm drainage system for a part of the area shown in the map below. So we are going to cover some area like this with a drainage network that is largely hypothetical. The topology of the network should look something like this. So this is what we are going to base our design on. So let's start. I'm going to move this document away and open the Swim software. EPS Swim 5.2 is what I'm using. So we start with create a new project, and we want to save this, save as. I will save it in a uh, new folder, uh, Colombo. Okay, network. So the first step is we want to change the units into cubic meters per second. Done. And then we want to load the backdrop map. Load. So this backdrop map is available here, my map PNG. And we also have a world coordinate file with that, my map. So, and then click scale map to background image. If you do that, then Swim will create a setup where geographical information is correctly projected into the Swim desktop. There you are. So the first step we want to do here is to make sure that the scale is correct. Very quick test you can do. First, of course, you have to set auto length to on. That is very important. And then what I'm going to do is to create two um, two junctions precisely on either side of. Let's zoom it a little bit. Okay, zoom to this one. Okay, and I'm going to create two junctions precisely on either side of this uh, scale bar. That way I can very quickly measure what is the true distance between these 2 points. So you create a conduit link and then double click on that and you can see the distance. So it's 1007. So that is good enough for us. Slightly off by 7 meters, that is not a problem. So before I forget, let me delete this. So we are set to go. Now let me zoom it out, covering the whole area again. So now the first step is let us create some uh, drainage uh, subcatchments. So uh, usually this is done in urban areas by looking at different blocks and in what direction the water would flow and so on. But for this exercise, we are going to follow our instructions. So let's start with subcatchment 1, S1 here. So the first subcatchment done, then the second one. So like this, we create all the subcatchments. When we do this, Swim will automatically calculate their uh, catchment areas. So it's very important to be somewhat precise in doing this. We need two more. The final one. Done. So our subcatchments are done. Now, in order for these things to appear a little bit clearer, I'm going to turn this backdrop into a watermark. That way it will de-emphasize the backdrop a little bit so that we can see things clearly. Now, if you look at the properties of the subcatchments, you can see that the areas are automatically calculated. 5 hectares, 11.9 hectares, 8 hectares, and so on. Now, then let's draw the uh, conduit network. For that, first we have to lay out the junctions or manholes. So junction 1, junction 2, somewhere here, junction 3, and junction 4, junction 5, 6, 7, 8, 9, and finally we need an outfall here at the C, outfall. Okay, now let's stop for a moment and give these subcatchments and the junctions uh, some good IDs. So to do that, you can click on the catchment, first catchment, and call this one S1, and this one S2, S3, S4, S5, S6. So subcatchments are named properly. Now the junctions. This is J1, J1, J2, J3, J4, 5, 6, 7, 8, 9, and we call this one out. Now we can display these ID numbers. To do that, you have to go right click on the canvas options and then annotation, show subcatchment IDs, node IDs. I will also click link IDs because we are going to add links very soon. And while I'm at it, I will increase the font size a little bit so that it's clearer. So here you can see all the ID numbers. Now let us go ahead and add the links or conduits. So the conduit number 1 is from J1 to J2, and then from J2 to J5, and J3 to J4, and J4 to J5. Then from here to here, and from here to here. Done. Now let's rename these things as well. You can give them pretty much any name, but let's follow the convention given in the exercise. C1, C2, C3, C4, C5, C7, C6, C8, and C9. So if you look at these conduits, you can see that the length is also automatically calculated. Now we need to connect these subcatchments into respective junctions. So again, in the real world, what we do is we look at the flow direction in these subcatchments and what are the most natural places for this water to be taken in into the storm drain system. But in this exercise, we are going to follow the instructions. So S1 is pouring into the um, outlet J2. So the moment you do that, you can see this dotted line connecting it. But before I go further, I want to also add the rain gauge because we can do this um, in one go. So add a rain gauge somewhere here, and we'll call this one rain gauge 1, RG1. If you want to show that, options, rain gauge ID, and you can see it's RG1. And then let's go and change this into RG1 and pouring point J2. Same RG1 pouring point J4. This is J7. Also J7, J7, and this one pours into J9. Okay. So all the subcatchments are now connected. The next step is to look at the um, geometry and dimensions of the conduits. So all these lateral branches are circular. So the circular fine max depth is 1 meter. That means 1 meter diameter circular pipe. So let's keep it as it is. So all these laterals are on that default value, but the central ones we need to change into rectangular open and maximum height 1 and bottom width 1. Let's first assume it's 1 meter by 2 meter, 1 meter by 2 meter canals. So I want to do that to this as well. Rectangular 1 meter by 2 meter. Oops, 2 meter. 1 meter by 2 meter. I'm sorry. This one also rectangular 1 meter by 2 meter. Right. So now we have our geometry. Uh, Next, we want to input our rainfall. So we have a rain gauge, but rain gauge at the moment does not have any values. So we are going to create a time series for rainfall. While we are at it, we are going to create two time series. So click on time series on top and then create one. The first one is 2 year 120 minutes design storm, right? So this one, if you go to the spreadsheet that uh, we have um, on the alternating block method calculations, you can see here, these are the values you need. So we need to copy these values into swim. So what I'm going to do is so in the time series you have here time 0, 15, 30, 45, 1 hour, 1 hour and 15, 1 hour and 30, and 1 hour and 45, and 2 hours. Done. And then we can directly copy the values of rainfall from here. So copy and paste. So the first value is 0. So the rainstorm looks something like this. Now we can do the same thing for the 10-year. Okay, so create another one. Um, 10 here, 120 minutes. Okay, and I'm going to copy the time from this one. Copy time and then copy the values from our spreadsheet. So to do that, we have to change the return period to 10 and then copy these values. Yeah. Okay, so now we have two design storms. So in the rain gauge one, we are going to use the 2-year one first. Now, there are a couple of other things that we have to make sure before we try to run this model. That is, go to Options, General, start here. So, process models, rainfall runoff, and flow routing. We are not going to consider water quality and snow melt, etc. You can. Then, infiltration model, we are going to use green amp model. The routing model is dynamic wave. This is the most comprehensive shallow water equation implementation that we have. So the rest is okay. Go to dates. Um, End analysis at 6 hours. So this is all right for the moment. Let's see how it goes. And then here, reporting time step, we want to make it smaller. 1 minute. Let's say every 1 minute we get the results. So um, these are also we can make them 1 minute. Routing step 20 seconds is okay for the moment. So let's stop it there. You have changed the default infiltration method. So all subcatchments will be changed. Yes. Now we will go back to our subcatchments and um, give some more important properties there. That is the impervious fraction, that is percentage impervious is 75 in all catchments. And these are very flat catchments, so we will leave the slope as 0.5. But it's very important to calculate the width also somewhat correctly, even though it's always an approximation in this case. Now, the typical way we do this in the real world is we look at the catchment in the field and see whether there are any channel networks. Then you get the longest channel as the length of the catchment and then divide the catchment area by that length. But here what you can do is, the water is flowing in this direction to J2. So let's consider this as the width. In this subcatchment, this as the width. And this one, something like this. Yeah, roughly. So looking at this scale, we are approximating here. So looking at this scale, you can see that the width, this width of this is about 200 meters. So let's make it 200. This also about that much, 200. And this one is double that, 400. This is also pretty much similar, 400. And this one, yeah, about 250. And this is also about 250. Right. So that's done. And then we need to do the uh, impervious fraction, 75%, 75%, 75, 75, and 75. Okay. Now we have to give the infiltration parameters. So this is a loamy soil. So if you look at, we need suction head and hydraulic conductivity for in units of millimeter and millimeter per hour respectively. Looking at the loam, it is about 89 and 7.6. So 89 and 7.6. Okay, and you change it to for all the subcatchments. Done. Yeah, 897.6 everywhere. Now we have to enter the elevation of the manholes, and so the invert elevations are given here. So let's use those numbers. J1 has to be 2 meters, J2 1.5, and of course maximum height is also important. 3 meters here, 3 meter, J3 2 and 3, J4 1.5 and 3, J5 1 and 3, J6 1 and 3, J8 1 and 3, J7 0.5 and 3, and J9 0.25 and 3. And the outlet, there's only one value, invert elevation. There is no maximum height in the outlet. Invert elevation is 0. So done. Now we have provided most of the important parameters. Let's have a quick check at the roughness of the conduits. So the value is Manning coefficient is about 0.01, which is a good value for smooth concrete conduit. So we can leave it as it is. And there are a lot of other parameters, but we are not going to worry about them just yet. So let's try to run it. But before running, let's go into rain gauge and see, okay, the time interval of the rainfall is 15 minutes, because you remember that the rainfall we input are like that, and then this is in volume, not intensity. So yeah, let's run the model. Run was successful. I mean, sometimes if you have forgotten certain things, this run may fail. Then what you do is a little bit go back and do a bit of troubleshooting, but this time it worked. So then the first thing maybe we want to do is to see whether there is any flooding. One of the easiest way to do that is go to the report and summary, and if there's flooding, there will be an entry called node flooding. So you can see there's quite a bit of flooding happening everywhere. So you can get a better picture of this by plotting a cross section, for example. So you start with J1 and then go to the end node of out and find path. So you can see this is our cross section, and then you can actually play the simulation like this, and it will show an animation of how the water is flowing. So you can see that there is a surcharge, and then here there is flooding. So we need a little bit bigger conduits than this. So one tip at this stage is to keep this uh, visual as it is, because the moment you change something and run the simulation, it will be automatically updated. So that's a nice thing to have. So, and also I'll keep the summary results as it is. We can have a look at it. So what I'm going to do now is first increase the size of these central conduits um, keeping the maximum depth, maximum height of the conduit as make it about 1.5 meters. Okay, maximum depth. You can change it here or in this dialog. 1.5. Fine. Let's run it again at this stage and see. So you can see the size increased. And if you look at this, the flooding levels have changed, but there is still flooding. So J2, J4, J5, J7. J2 and J4, these are flooding. So let's try to make these conduits a little bit bigger. Circular, maximum depth 1.5. Circular, diameter 1.5. And see how we are doing. So still uh, J1 and J3 flooding amounts are very small. We can almost ignore them, but J5 and J7 has considerable amount of flooding. So that means we need to increase the size of this 1 to 2 meter, let's say, and this also to 2 meter. Okay, let's move further and try to reduce these flooding events, especially at J7. We can see there is a significant volume of flooding happening. So, and J1 and J3 I would ignore because these are very small values, but J5 and J7 we have to investigate further. So, to make it easy, I will just keep this as it is and create the graph of flooding of these locations. So, um, notation, node IDs. Okay, um, J5. So not the depth, but I would use flooding, right? And then J1 also, just for fun, and then J7. So all the 4 nodes that are flooding will produce a graph. So you can see that the flooding level of J3 and J1 are very tiny, so we can ignore them, but these are a little bit bigger. So the central part is still flooding. So what I would do now is go and increase the size of these conduits a little bit further, 3 meter wide. You can try 2.5, it might work. So now you can see there is no flooding at all. And if you go here, you can see that summary results no longer have flooding because there's no flooding anywhere. So you can validate this further by looking at this cross section. And if you want to see the other branch also, you can create 2 cross sections, one like this, the other one starting from J3, start node J3, end node out, find path. Okay, there is this one. So now we can display both those together and then um, play the simulation. So So there is no flooding, but there is some surcharging. So if you like, you can increase the conduits a little bit more. But for the moment, we can assume that there is not no flooding going to happen. So that's it, folks, about this simple storm drainage system design for an urban area. Now let's try to see what is the situation going to be when we have the 10-year storm. So I will stop this and then um, go to my rain gauge and change this into 10-year storm. Simple as that. Then when you run it, you can see now they are going to be flooding because the uh, rainfall amount is bigger. So uh, report status, you can see that nodes um, J1, J3 has minor amounts of flooding, but J5 and J7 has substantial amounts of flooding. Uh, if you want to display these flooding nodes on the map, you can do that. Um, how you do that is you go to options, annotation, then don't show the node IDs, but show node values. Okay. And the node value, instead of invert, we'll call it uh, flooding. So flood flow at a given time. And you can also change this color ramp a little bit with auto scale and so on. So usually what I would like to do is actually change this first color into white. Okay. And then um, yeah, something like this, so that whenever there is flooding, there will be color. Otherwise, it's white. So now we can play this and see whether there is any flooding. If you want to see it a little bit clearly, you can also increase the node size like this. So still no flooding. Yes, now you can see flooding happens around this. Now, yes. So a little bit of flooding here, but a lot of flooding happens in J7. So this is a critical place. You can see at in J5 also, it's only for a brief moment in one time step. That's it. But in J7, there is continuous flooding for an extended period of time.